Okay, hello again. So we're still on to series. We're on lecture 8, and we're still actually in section 11.2 for those of you who are in my class and following along with the textbook. We talked about geometric series in some detail. Geometric series are perhaps the series that we can work with most easily because we can tell exactly when they converge or diverge, and we can tell exactly what they converge to in that situation. Most series are not so good. We're going to, in the rest of chapter 11, or a good portion of chapter 11, we're going to come up with sort of theorems that tell us when things converge or diverge. But even with those theorems, we often won't know what they converge or diverge to. We'll only have estimates of that. And the first such theorem is the test for divergence. It's perhaps the easiest. So let's suppose we've got a situation where we've got a series that converges to some number L. Now let's first just consider the situation where all the terms are positive. So I start with A1. Notice I've got a number line here. I've got A1 on there, and I've got L. If all the terms are positive, well, I'm going to add A2 to that, right? So I went from 0 to A1, and I'm going to add A2, and I get this next A1 plus A2, and I'm going to add A3, and I get A1 plus A2 plus A3, right? The next partial sum, that's going to be S3. I'm going to add A4. I'm going to add A5. What can you tell me about those things? They've got to get smaller and smaller, right? AIs have got to go to 0 in order for them to not pass L. Well, the same is the case if some of the AIs are, in fact, negative. So let's look at a slightly different situation. So we've got A1. Let's make that over here. So we got like A1 here, and oh, I don't know where 0 is. Let's say 0 is down here, so A1 was positive. And maybe A2, so A1 comes here. And maybe A2 is also positive, and it jumps way over here. Now, of course, if all of the A's are positive, I'm never going to get back to, so this is going to be S2, which is A1 plus A2, right? A1 here is actually equal to S1. If all of the terms were positive, I would keep going forward. I would never come back. So there's going to be some terms that are negative, right? So in this case, S3, I've got it, in this particular example I'm doing, my A3 happens to be negative. I go backwards. And, you know, maybe I've got a couple of negatives, but eventually I've got to come back this way. I need another positive. Let's just make A4 be positive so I get to S4. And what happens here, if I'm going to zero in on L, what's happening to the A's? Well, they might be bouncing back and forth between negative and positive, but still the A's are going to 0. In fact, the first theorem we have about convergence, well, the second. The first has to do with geometric series, but the second is that if the AIs do not go to 0, then this thing here, this series, I equal whatever you want to infinity of AI, diverges. So in order for it to converge, the terms have to go to 0. If the terms don't go to 0, it definitely does not converge. However, the converse is not true. So the converse of this is not true. There are series with an I, some I equals some point to infinity of AI, for which the terms AI go to 0, but the series diverges. So this test is only a test for divergence, not a test for convergence. So, for example, if I look at this series here, sum I equal 2 to infinity of I over I plus 1, I notice that I over I plus 1 goes to what as I goes to infinity? That goes to 1. Therefore, this series diverges because it doesn't go to 0. The terms don't go to 0. The terms go to 1. Therefore, it diverges. So this is merely a test for divergence. If the terms do not go to 0, the series diverges. If the terms do go to 0, as we'll see in the next video, it may or may not converge. Okay, and we'll look at a classic example of a series whose terms go to 0 but does not converge in the next video.